Okay, to recap what we talked about in when you're solving physics problems, how to show your thinking clearly and fully. You are always going to start with the equation you're using, and that equation should be variables only. Then you're going to show your substitution, and you're going to have your answer, and your answer must have proper units. So the units we have used so far this year are meters, seconds, and kilograms. These are the base meters, the base units, that make up all of the other units we use, or we have been using so far. So then we have newtons, and that's what we use for force. And for energy, we have joules. And then for impulse and momentum, we have a kilogram meters each second squared, or a newton times a second. If you are doing forces, you should have a force diagram, even if it doesn't ask you to draw an official one, and you should use some of the forces equations. A lot of the questions I'm going through with people, if you had just drawn your force diagram and written your sum of the force equations, then you would be able to solve the problem. If we are doing energy, you should have your conservation of energy equation. And if it's momentum, if it's a momentum of a system of objects, you should have your conservation of momentum equation. For kinematics and projectiles, I highly suggest the T-charts and a diagram to help you visualize the situation. Okay, let's talk about the inferred information. So if it mentions the object is in equilibrium, your net force is going to be equal to 0. And your acceleration is going to be equal to 0. If the object is at rest, your net force is going to be equal to 0, and your acceleration is going to be equal to 0. If the object moves with constant velocity, again, you're going to have a net force of 0 and an acceleration of 0. This is what we refer to when we call forces balanced, or we say the forces are balanced, or it's a balanced forces situation. The object is slowing down is where we get into the unbalanced forces. So this is where you're going to be looking at your net force of being mass times acceleration. So we're going to use the second law. And then remember, if you have a positive velocity, in order to slow down, you have to have a negative acceleration. If you have a negative velocity, then you have to have a positive acceleration. They have to have opposite signs for the object to slow down. And remember, negative is just the direction. All right, speeding up is the opposite. The acceleration and the velocity must have the same sign if you're going faster. Okay, that's the only way to increase your velocity, is if the acceleration is in the same direction. If we're moving across a rough surface, sliding, I guess would be a better word there, we are talking about kinetic friction. And kinetic friction will always be equal to the kinetic friction coefficient times the normal force. Okay? If it's constant velocity, then whatever force is pulling it, the friction has to be equal to that. if it's being pushed with a force of 10 newtons or anything that's less than what we call the maximum static friction force, then the object will remain at rest. So this is a static friction situation. And now, if we're looking at static friction, this is really a less than the mu for static friction times the normal force. Your frictional force on for something that's static friction, you're going to want to look at the sum of the forces equations. And you're also going to want to look at the sum of the forces for the kinetic too, because most of the time they're probably not going to give you these coefficient of frictions. They're going to want you to find friction, and then they're going to want you to use that to find the coefficient of friction. So here in this situation, the static friction force would be 10 newtons. If you pushed with a force of 15 newtons and it remained at rest, the static friction would be 15 newtons. And the static friction is going to match whatever that other force is up until you reach that threshold of the maximum static friction force. And then it is going to be equal to the mu s Fn. Only for that one instant, an object will start accelerating and it goes to a kinetic friction situation. Okay, we're still using mass times acceleration, but now we're talking about centripetal acceleration. And we find centripetal acceleration by taking v squared over r. Okay, so these are kind of things that are embedded into questions that you have to know how to treat them. All right, moving on to projectile motion. So all these phrases have to do with projectile motion. If I propel something horizontally, the initial vertical velocity is 0. The acceleration is whatever acceleration is due to gravity. If you're on a different planet, then we won't use the acceleration for Earth. But on Earth, it's about 10 meters each second squared. Remember, we've talked about it being 9.8 is the more accurate value, but because of the time constraints in the AP test, the College Board lets you round it off to 10 for easier simplifications. Okay. If we just drop an object, we are releasing it from rest. So again, that vertical velocity initially is going to be equal to 0. If we throw something upward, it is going to be still acceleration due to gravity. And same with something reaching its maximum peak. That acceleration never becomes 0. The thing to know is that if you have an overall vertical velocity of 0, then your final vertical velocity is going to equal the negative of your initial vertical velocity. Okay, again, that's symmetrical projectiles only. And so they have to start from and land back at the same vertical position. It doesn't mean they have to land back in the exact same starting point, because you can have a horizontal displacement there. So for example, like a projectile that looks like this starting point and this ending point are the same vertical position, but you do indeed have a horizontal displacement or a range. So when we're talking about this maximum peak here, the Vy equals 0 at maximum peak, but the overall velocity is equal to whatever your horizontal velocity is there. Because if I had all 0 velocity there, I would have a projectile that goes up and then immediately falls straight down when it gets to its highest point. And that is not what we see when we see projectiles. Okay, the last one here is an object starts from rest. Its initial velocity will be 0. If it says stops or comes to rest, then we'd be looking at a final velocity of 0. Last but not least, I have found for the most part that students know, once they know what concept to use, they don't seem to have a problem there. It's figuring out what to do or what concept to use. So we also talked about the velocity at the bottom of something. That's usually going to be an energy problem. That's going to be the shortcut way to do it. But you could also do it with a combination of forces and kinematics. It's just going to depend on what the situation gives you for information. So, for example, if it's a projectile and you're looking for the velocity at the top of the path or the bottom, then it's probably just a kinematic problem. But if you are doing a problem like on an incline or like a roller coaster, you're going to need some sort of combination of forces and or kinematics, and possibly in the case of a roller coaster, some sort of circular motion. Collides or collisions is going to be a momentum or an impulse problem or a combination of the two. If something is launched, it is a projectile. Or kinematics problem. If it's launched straight up, comes straight back down, something like that. Compressed or stretched spring, elastic potential energy, which is 1/2 kx squared, or Hooke's law, which is kx. And in this case, the k is the spring constant. And the x is the stretch or compression of the spring. And that is the stretch or the compression from equilibrium length. We are going to talk a lot more about springs when we do simple harmonic motion. We've seen a little bit of springs. You're going to see a lot more. It is coming. Also, the rolling, and this is a rotation problem. And so we will be doing more rotation when we come back. That's what we're going to start with second semester. Oops. Did not mean to draw that line. Okay. Last but not least, these three down here. This is going to be a circular motion problem. So remember, it doesn't necessarily have to look like a full circle. This point right here in the dip is part of a circular path. So sometimes they will look at that, or going over a hill can also look like a circular path. So you could use it for that. All right, string rope chain incline is going to be a tension. And then, the string rope chain will be a tension, and this incline, you're probably looking at a normal force. That is equal to mg cosine theta, as long as there are no other vertical forces. And you're going to have to do some of the forces equations, because we do not have equations for tension or the normal force. You have to make that equation from a force diagram and some of the force equations. All right. And then change in energy is equal to work. And an important thing to note there is that a lot of the questions you're going to see are going to have you looking at work as the change in energy. You're not often going to be given a force and a distance and ask for the work done on something. Typically, they stress it more as a change in energy, so you should understand that those work together. Okay, I also talked about an equation list for some derived equations. And so that is this page. If we go back to the beginning of this page, it is here. The things we have done right now are the kinematic equation here. Remember, you can get that from combining two of the kinematic equations to get rid of the acceleration. Vector resolution, usually for velocity, but could also be for displacement. Remember, we're always dealing with an angle there. So if you're given a horizontal and vertical velocity and you're finding an overall velocity, it better have an angle on it because it's a vector. The ramp problem, remember, this is no other vertical forces. When the normal force equals that. So for example, if somebody started pushing down on that box, or there was a tension pulling up in the direction of the normal, then that would change things a little bit. The bank turn, you should understand that one. We talked about it in class. If you have your car here, remember the center of your circle is this way. So you have to resolve the normal force into components instead of the gravitational force, okay? So this becomes a force diagram that looks like this, Fn, Fg, and if it has no friction on it, what you're going to want to do is put your axes like the, sorry, not like that. I literally just said that we're not doing that way. Your axes are going this way and this way because your net force is going to be along this axis right here, which is going to be the horizontal component of the normal. So once you do that, then you figure out that Fn cosine of theta equals mv squared over r, and your Fn sine of theta, and I might have those backwards. Hold on. Yeah, I think this one becomes, no, I think that might be right. Oh, I do have my angle in the wrong spot. Oops, I didn't mean to erase that. And then I erased it again. It's going to be one of those days. All right, I think that's my theta. So I have my sine and my cosine backwards. So it is going to be Fn sine of theta equals mv squared over r. And Fn cosine of theta equals mg. So your Fn, then you solve for Fn, substitute it back into the other equation. And so that's kind of where these relationships came from, okay? Because if I take, I do not know why I keep drawing random lines. If I take these two equations and combine them, I get Fn equals mg over cosine of theta. And so then I get mg over cosine of theta times sine of theta equals mv squared over r. The m's will reduce out and you end up with g tangent of theta equals v squared over r. And so that's where these equations come from. Okay, and then circular motion, gravitation. Again, these are equations. You need to know how to derive these in order to get full credit for them on a short answer or free response question. Second page of this is second semester for the rotational kinematics. The oscillations are also second semester, so you don't need to worry about those right now. Remember that kinetic energy is conserved only in elastic collisions. Or perfectly elastic collisions. This equation here is also the equation for inelastic. So inelastic collisions will look the same one. The equation will look the same way. And they're using the prime here as a finals. I'll just write it the way they have it written. So the only way to know whether it's elastic or inelastic is to look at the kinetic energy before and the kinetic energy after. Okay, so be aware of that. Not all bouncy collisions are elastic collisions. All right, we also talked about explosions. One of the questions came up that if you have two things that they're moving and then they separate, yes, there has to be some sort of force acting in between the two objects. But remember, third law tells us that the forces are equal in size, but opposite in direction. So the same force acts on both of them, and it's internal to the system. So kinetic energy might not be conserved, but the momentum certainly is. And then there are no waves and no Doppler effect in AP1 anymore, so you don't need those. All right, a quick reminder about graphing. All equations on the equation chart are in y equals mx plus b format. I am just going to look at this first one here. So if you had this graph here, well, if you look at the equation for kinetic energy, you'll see that it's 1/2 mv squared. And so in order to linearize this graph, you wouldn't change KE because in the equation it's still just KE, but velocity squared is what's in the equation. So if you were to graph that, you would get a straight line. So the graph is now linearized. The next graph down is that graph. And so again, the equation for kinetic energy is 1/2 mv squared. If this is my y-axis and this is my x-axis, well, everything is in that y equals mx plus b format. So y, x, here's my slope. So my slope to this graph would equal 1/2 of the mass of the object. So thinking about those things, whether you take the area under the graph or the slope of the graph, you can look at the equation. So if I had an impulse, which is a force times time, and this graph right here is a force times or a momentum times time graph, well, I would divide these according to this equation. So the change in the momentum over the change in time equals force. So the slope of this graph would be the force. And remember, that's an average force there, not necessarily the force the whole time. You could also do the same thing if you had a force versus time graph and you had a graph that looked like that. Well, momentum equals force times time. So if I multiply these two together, I would get change in momentum. So this is going to be an area. And the area of that equals the change in momentum. All right, I hope this helps.